This is Srikanth S, Assistant Professor of EEE Department. In this session, I am explaining about three-phase AC circuits. How generally how AC power, AC is nothing but alternating current. How an alternating power which is going to generate, that is here based on the magnetic flux, based on the magnetic flux lines, we are going to get the alternating current supply. In this, it whatever the supply generation, how the voltage generation is depends on the Faraday's laws of electromagnetic induction. That is, the Faraday's law is nothing but whenever a conductor cuts the magnetic flux, an EMF will be induced, and that EMF is proportional to the rate of change of flux linkages. Here, let us consider how the flux linkages and how we are going to generate the voltage. Let us see. Here, this is the flux phi b, that is flux density into area, that is equals to flux density into area into cos phi, where cos phi is the angle between the flux lines and the whatever the conductor which we are placing together. So here the cos phi value will be decreases, which is when the cos phi value will be 1 at 0 degrees, and it goes on reduces when cos phi value is 0 at 90 degrees. So here we are going to have the decrement in the flux when the rotation is taking place. Here the flux depends on the orientation of surface with respect to the B field, with respect to the magnetic flux density field. And here the induced EMF in a closed loop equals negative of time rate of change of flux through the loop, where Faraday's law, from the Faraday's law, E is equals to minus d phi by dt volts. Here you can see whenever the conductors are placed, this is north and south pole conductor, this is north and this is south, and when the conductor rotates, when the conductor rotates inside the magnetic field, when the conductor rotates inside the magnetic field, an EMF will be generated. So here note that flux whatever the flux changes, phi b is equals to b into a, vector b into a, that is equals to, that is area of cross section which is taken by the conductor. A is the area of cross section which is taken by the conductor. B into a, that is equals to b into a into cos phi. For phi is equals to omega t, EMF which is generated is equals to BA into sine omega t. Here, whatever the sine waveform which we are going to get, that will be converted into a DC by using the brushes. These brushes are going to convert the voltage from AC to DC, which are going to have, these brushes are going to have the slip rings, and these slip rings are going to be connected to the commutator, and this commutator is going to convert the AC supply into the DC. And here when the flux is more, when the flux cutting is more, then the EMF will be high. When the flux cutting is less, the EMF will be less. So here, whenever we are taking, whenever we are taking the changes in the conductor positions, so at this position, the voltage which is induced is zero. When it is because the flux cutting by the conductor, when the conductor is placed vertically, what is the flux? But here, what are the conductors which are placed vertically? The flux cutting by the conductors is less. Flux cutting by the conductors is less. So the EMF is less. When it is turned by 30 degrees, when it is turned by 30 degrees, the flux cutting will increase. So when the flux cutting increases, the EMF will increase. Like this, if we go on increase the voltage at 90 degrees, that is the maximum flux at this position, maximum flux is linking with the conductors. Maximum flux is linking with the conductors. So the maximum EMF will be developing. And this will goes on until the conductor is reverses its polarities. And once it is reversed, again the negative voltage will continue if you go on changing the positions of the conductors. So this is for the first conductor. And when we want to go for the operation of the next waveform, that is uh, in a three-phase system, in a three-phase system, each and every phase is displaced by an angle of 120 degrees. Each and every phase is displaced by an angle of 120 degrees. That is Vm is equals to, V of t is equals to Vm sine omega t. V2 of t is equals to Vm sine omega t plus or minus 120 degrees. Every wave in the three-phase system is going to displace by an angle of 120 degrees. V3 of t is equals to Vm sine omega t plus or minus 240 degrees. Like this, we are going to have the change in the waveforms with a displacement of 120 degrees. And this we can draw the phasor diagram like this. This is the VA phase, VB phase, and VC phase. Each and every phase is displaced by an angle of 120 degrees. Here you can see how a three-phase voltage is going to be generated. And here we are going to have 6 number of slots. These are the slots. A, B, C are the slots. A dash, B dash, C dash are the opposite slots. And these are connected A, B, B, C and C, A are connected. When the rotor, this is having the rotor which is having the conductors with the north and south poles magnetized, and when the rotor rotates, which is going to generate three-phase output, because if a conductor which is having a single flux, that is single conductor, then we are going to get a single AC voltage. When we are having a conductor with three-phase connection, that is here the magnetic field with the rotor, and these are the three-phase conductors which are placed. When the magnetic field rotates inside the conductor, according to Faraday's law, an EMF will be generated in all the conductors. So all the conductors are connected in a manner such that which has to generate a three-phase voltage, and each and every three-phase voltage will be displaced by an angle of 120 degrees. VAA dash is equals to Vm, the maximum voltage, which is represented with root 2 into V, because the V is the RMS voltage, root 2 V cos omega t. VBB dash is equals to root 2 into V cos omega t minus 120. VCC dash is equals to root 2 into V cos omega t minus 240 degrees. Here, three-phase voltage can also be generated with three single-phase voltage. We can also generate the three-phase voltage with three single-phase voltages. And these are the two methods of source connections. One is star connection, one is delta connection. Here, the star connection is going to have a common point between all the three phase voltages, all the three phase voltages, that is VAN, VBN and VCN. The negatives of all the three voltages are connected together, which is going to form a star connection, and wherever the point which is taking, that we are taking it as a neutral connection. And in the same way, we can also connect the positive of one voltage is connected to the negative of another voltage. Like this, VBC positive is connected to negative of VAB, and VAB positive is connected to negative of VCA. When we have connected in this manner, in a loop manner, then that will form a delta connection, which is going to have the phase A, phase B and phase. This is These are the voltages. VAN is equals to, we can write it as VP at an angle 0 degrees. That is, always one voltage will be taken as the reference voltage, that is at 0 degrees. VAN is equals to VP at an angle 0 degrees, and VBN is equals to VP at an angle minus 120 degrees. VCN is equals to VP at an angle minus 240, that we can write it as VP at an angle 120 degrees. Here the voltages between the lines ABC and the neutral line N are called phase voltages, which is whatever the voltages between the line and neutral line, that is between A and neutral, whatever the voltage is called, that is called a phase voltage. If the voltage between AB, BC and CA are called, between the lines are called the line voltages, and in star connection, in star connection, the line voltage and phase voltage are different. Phase voltage are different. Whereas in delta connection, the phase voltage and line voltages are same. Phase voltage are is equals to line voltages. Here, when we take VP at an angle 0, that is VP into cos 0 plus VP into sin 0, which is equals to VP, and VBN is equals to VP at an angle minus 120. If we substitute VP cos minus 120 plus JVP sin minus 120, which is equals to Vp into minus 0.5 minus 0.866 J, and VBN is equals to Vp at an angle 240 degrees, that is Vp at an angle 120 degrees. So if we substitute the values Vp at an angle, Vp cos of minus 240 plus JVP sine minus 240, which is equals to, we are going to get Vp minus 0.5 plus 0.866 J. If we add all these three together, which is equals to 0, and this is called a balanced voltages. This is called the balanced three-phase voltage. Here, this is the way we are going to have the balanced phase voltages are equal in magnitude and are out of phase with each other by 120 degrees. That is, there are two possible ways in which a source can be balanced. That is, VAN is equals to Vp at an angle 0, VBN is equals to Vp at an angle minus 120, and VCN is equals to Vp at an angle minus 240. This is every time the voltage, all the three voltages are displaced by an angle of exactly 120 degrees. Then those connections are called balanced connections. That is, these connections can be having the positive ABC sequence or ACB sequence, that is called negative sequence. That is called negative sequence. That is, here VAN, VBN, VCN. Here we are having VAN, VCN, VBN. In any way, you can connect the whatever the three phase voltages which we are having, all the voltages are displaced by an angle of 120 degrees, then those connections are called the balanced voltage or balanced supply. And this is the way how we are going to have the star to delta connections in the same way what we have done in the star to delta transformation while calculating the equivalent resistance. That is, whenever we are having the balanced voltages, whenever we are having balanced voltages, we also need a balanced load. The phase impedances are equal in magnitude and in phase. Whenever we are having all the impedances or all the resistances are equal, then those loads are called the balanced loads. That is, here we are having Z1 is equals to Z2 is equals to Z3, which is equals to ZY, where if we want to get the Z delta, 3 into ZY is the voltage, or ZY is equals to 1 by 3 into Z delta. If we are taking the delta values and to calculate ZY, that is 1 by 3 into Z delta. Here in star connected, what are the voltage, how the voltage parameters are going to change between the and phase voltage and line to line voltage. Here this is phase A, phase B, phase C, and this is neutral A, B, C. This is VAN, VBN, and VCN. Here the phase voltage is the voltage between the neutral and that particular phase. That is VAN, which is equals to VBN, which is equals to VCN. These are the three phase voltages. These are the three phase voltages which are equals to phase voltage. Okay, these three are the phase voltages. Now we need to calculate what is the line voltage between A and B. What is the voltage? That is equals to, if let us consider this phase voltage as VP and here VAB as line to line voltage, let us consider that is root 3 times the V phase voltage. Root 3 times the V phase voltage. And here the current which is flowing IA, IB, IC. There is no other path for the current. Only one path is there. So the line current is equals to the phase current. Line current is equals to the phase current in the star connected three phase circuit. Here the line connected three phase circuit, the phase voltage is the voltage between the phase and neutral, and line to line voltage or line voltage, that is equals to root 3 times the phase voltage, and line current is equals to phase current. And voltage is in a delta connected three phase circuit. In delta connected three phase circuit, here this is the voltage, that is VAB, this is the voltage VBC, and this is the voltage VAC. So these voltages are directly connected to the voltage VA, VB, VC, because if you see the circuit, VAB is connected between the terminals. Let us consider these are the terminals 1, 2 and 3. So VAB is the voltage which is connected between 1 and 2. That voltage is same as the VB voltage. That voltage is same as the VB voltage. So here in delta connected system, both line to line voltage and phase voltage are same. Line to line voltage and phase voltage are same. So V line to line is equals to V phase. Here whereas the line currents is equals to, here the line currents is equals to IL is equals to root 3 times the I phase. Root 3 times the I phase. Whereas in star connected, line voltage is root 3 times the phase voltage. Whereas in delta connection, line current is the root 3 times the phase current. Remember these formulas. These are very important corresponding to the three phase circuit. And these are the single phase and three phase power equations. That is S is nothing but complex power, that is equals to V phase into I phase. So P is equals to active power, that is equals to V phase into I phase cos theta or cos phi, and Q one phase is equals to V phase into I phase into sin theta. This is the reactive power. Q is nothing but reactive power, and this is the power triangle. P is equals to S cos theta and Q is equals to S sin theta, and this is the S value. And in the same way, we are going to have the three phase power equations, that is S complex power is equals to 3 into V phase into I phase, and P is equals to 3 into V phase I phase cos theta, and Q is equals to 3 into V phase I phase sin theta. So these are the single phase and three phase power equations. And whenever we want to go with the line voltages, these three phase voltages, whenever we want to go with the line voltages, for star connected load, IL is equals to I5 and VL is equals to root 3 into V phase. Root 3 into V phase. If we substitute in place of V phase, VLL by root 3, that is 3 into V phase into I phase into cos theta, that is equals to 3 into V line to line by root 3 into IL cos theta, which is equals to root 3 into VLL into IL cos theta. For delta connected load, for delta connected load, IL is equals to root 3 into I phase and VLL is equals to V phase. That is, the three phase power is equals to, here IL by root 3, we have to substitute 3 into V phase is same as line to line voltage, but I phase is equals to IL by root 3, which is equals to root 3 into VL IL cos theta. So here, whenever we are writing the three phase power equations in terms of line quantities, we are going to have the power equations as root 3 into VL IL cos theta and Q is equals to root 3 VL IL sin theta, and complex power is equals to root 3 into VL IL. This is about uh, the three phase equations and three phase circuits, and how we are going to have the three phase supply, and what is the displacement between the phase voltage and line voltage. Now let us go with the source transformation. Source transformation is a technique which is used to convert one kind of source into other. Generally, we are having two types of sources. One is voltage source and another is current source. So, whenever we want a current source from the voltage source, we can convert, and a current source and a voltage source from the current source, we can convert, because if we don't have the possibilities, we can convert by having some other, by adding some parameters or some elements to the circuit or some elements to the source, we can get the source transformation. That is, here, whenever we want to transfer a voltage source into a current source, whenever we want to transfer a voltage source into a current source, when a voltage source in series with the resistance, when a voltage source is in series with the resistance, that is nothing but, if let us consider a practical voltage source, a voltage source will be having a small resistance, source resistance in series. So this, when it is connected in series, and this will be transformed into a current source, this will be transformed into a current source in parallel with the resistance, in parallel with the resistance, where the current source magnitude is equals to voltage divided by that particular resistance, where I is equals to V by R. I is equals to V by R. Let us take the example. That is, if we take 10 volt source is in series with 5 ohms, the equivalent current source will be a current source where I is equals to 10 by 5, that is equals to 2 amperes, and which is connected in parallel with the resistance, that is 5 ohms. And in the same way, whenever we want to convert a current source into a voltage source, we can convert a current source in parallel with the resistance, that is, that can be converted into a voltage source where the voltage is equals to V into IR. Sorry, V is equals to I into R, that is in series with the resistance, that is in series with the resistance. So here the voltage current source can be converted into a voltage source by multiplying that current value with the resistance which is connected in parallel to it. And let us go with the example. If let the 10 ampere source is connected in parallel with the 10 ohms, so 10 into 10, that is equals to 100 volts, which is in series with the 10 ohms. This is the current source converted into a voltage source. So in this session, we have discussed the three-phase AC circuits and how the three-phase voltage is generated, and what is the difference between star and delta connected source and load, and how we can transform a voltage source into a current source and current source into a voltage source. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.